So what we have learned in the past 3 weeks, we basically learned, well, just like the title of our class, signals and systems. So what we learned were signals and systems. What did we learn specifically about these contents? I think first of all, we learned that there are different kind of signals. They are all functions of independent variables called time, but there are, for instance, continuous time versus discrete time signals, right? They're all functions of time, but in the case of continuous, our t is taking any real value. But so that's why we usually write x of t. But in the case of discrete time, we are actually having the time variable only taking integer values. And in those cases, we have the special notation x of n. So not only the time variable has changed from t to n, the notation has changed, but also the parentheses have been changed to squared brackets. So that's the first difference. We have also learned periodic versus aperiodic signals. In the case of periodic, that means, let's again use continuous time as example. That means if I look at any time t and I shift it by a capital T period, and then I will end up having the same signal output, readout. So that has to be the case for any t, okay? So that means t is a period, okay? It's a period, not necessarily z period, because there might be, if a t is a period, then multiples of t is also a period. Okay, so that's what we have learned. So in the case of the discrete time, we use the different notation, and we use x of n plus capital N, right? So it's very similar. And then in this case, it's x of n. So this has to occur for any n. So so n is a period, okay? But in the first case, we learned that this t has to be positive, right? But in the second case, n is positive, but n is also an integer, right? Right. So that's what you face in the homework problem. For when you are determining the periods, right? Okay, so, and we also learned the fundamental period, right? So the smallest such period is called the fundamental period. So, smallest such t becomes t sub 0, that's called t naught. And then similarly, this smallest period, right, is a fundamental period in both cases. So certain things we didn't talk about, but you have learned in the past is digital versus analog versus digital. So what is the difference here? The difference is very similar to discrete time and continuous time. But here, we're not talking about whether the independent time variable is taking continuous or discrete values. We're talking about the signal itself. Let's say the amplitude, okay? In the case of analog, x of t can take, any continuous or infinite amount of possibilities. But in the case of digital, this is x of t only takes, finite values, okay? For instance, binary signals that are either 0 or 1. So this is nothing to do with the variable t. This is just x of t itself, okay? That's about the signals. And then about the systems, we actually only spent one lecture and we only learned two system properties, right? And one system property is about time invariance. The other property is about linearity. Okay. And what about time invariance and time linearity? By the way, if you have any question, feel free to unmute yourself anytime. And in the case of time invariance, you know, we're talking about some transformation of the signal as an input to the system lead to the same transformation of the output, right? So in this case, we're dealing with something we have learned. That is the transformation. So you can transform signals, for instance. So these dashed lines are transformations. There are a lot of different transformations we learned in the first week, a so-called affine transformation of independent variables, or in short, playing with time. Okay, we scale time, we shift time, and reverse time. So these are three elementary ways to transform time or playing with time. So there's one elementary transformation that's called time shift. Okay, so in that case, I have x of t minus t naught. If t naught is positive, I'm delaying. If t naught is negative, and then I'm time advancing, right? So I'm moving the signal horizontally left or right, but vertically, I'm not changing the signal. It's about playing with the time, what's in the parentheses. So in this case, what time invariance means is that, let's assume that our system, right? So usually what a system means is that if you feed an input x of t, the output is y of t. So this is a this is a continuous time system by default, okay? So in short, we can write a notation which says that, well, x of t results in y of t. So that's the notation saying that we have the input-output relationship. We skip the system in between, okay? So a time invariant system means that if I shift that x of t by t naught, if I shift the time, okay? For a time invariant system, the corresponding output is y of t minus t naught, okay? So this arrow here and the arrow here mean the same thing, means that the same system input-output relationship. So it means that for time invariant system, if you shift the input, the output would be time shifted in the same way. So this is what time invariance means. It means that the system behavior will not change. It will only be shifted, but it will not be changed. For instance, if you measure a RC circuit, the voltage around R or C, and the input is you turn on the power at time 0, then you measure the output, right? So you will get a signal shape, right? But if you turn on this power not today, but tomorrow, well, you will get the same response, but the starting point is not today, but tomorrow. So it's only time shifted, but it's not changing otherwise. This is what time invariance means. But also keep in mind that we have other elementary transformations that are nothing to do with the system properties here. For instance, time scaling and time reversing, okay? Reversal. So we'll give you more examples, but they are nothing to do with these system properties. In fact, if you scale or reverse time, right? If your system scale or reverse time, you will find out that the system is no longer time invariant. We'll see that, okay? The second property of systems we have learned is called linearity. So this means this is not playing with time though, it's playing with the signals. Okay, it's like analog versus digital. It's about the signal itself. Okay, so linearity basically means that, if you scale, so again, let's assume we have such input-output relationship, okay? Then for a linear system, what we end up having is if you scale the input, the output will be scaled. That's right. That's called homogeneity. Then if you add x1 and y1 together, let's say x1 and x2, excuse me. And let's say x1 result in y1 and x2 result in y2. Then the output is simply y1 plus y2. Okay, so that's additivity. And then we can combine these two expressions, homogeneity plus additivity, into linear combination. So that means if I scale x1 and x2 and add them together, the output is a y1 plus by2. So it means that for a linear system, if the inputs are linearly combined, then the output, the new output, would be the linearly combined original outputs. So it's that simple, okay? And now I think it's time to give you a few examples. Let's start with the elementary time transformation. Before I start, is there any question? Okay, so let's give a very simple example. Again, it's very similar. Example 1. So this is about elementary time transformation, okay? So one key mistake that people make a lot is what's the time shift parameter when the time shift is after time scaling or time reversal. So we have seen in the homework, for instance, we have a signal like this. And from -1 to +1, and the height is 1/2, 1. So this is x of t, right? So you know that, this can be transformed in multiple steps into any x of a t plus b, right? In 3 steps, right? In these 3 steps, you are combining, the elementary, 3 elementary, that is reversal, scaling, and shift. So in total, you have 3 times 2 times 1 equal to 6 orders. So 3 paths, but all leads to the same. Okay. So in other words, in the homework, you were asked to transform it in 2 different orders, but you should at the end see the same signal. If you see they are different, that means at least one of them was a mistake. Okay. So if I'm asking you to time shift first, you always know that your first step is change t to t plus b. So you will get xt, right? So let me give you a specific example. Let's say our goal is from x of t, multiple steps, right? Sorry, this arrow is not input-output relationship, okay? So this is just a change. Let's say we want it to become x of -2t plus 1, okay? So if you're doing time shift first, that's very easy. So I'm not gonna do that. So you're gonna do xt plus 1 first, okay? So I'm gonna do this order. I'm gonna do time reversal first. I will change t to minus t. So that will give me x of minus t, okay? And then I will time scale. I will change this new t to be the new t, right? T becomes 2t. So that's x of minus 2t. And eventually, I will get x of minus 2t plus 1. But how should I do the time shift here? So that's a common mistake, right? Okay, so let's do that later. Let's do the time reversal first. So we have the original signal as this. And then when you do the time reversal, it's really like changing the direction of time. So the signal is mirror imaged, right? So 1 is now at -1, and the -1 is now at 1. So this point is going to be here, and this point is going to be here. So it's like a mirror image. Right? Don't they look like mirror image of each other, right? Okay, now time scaling. So in the case of time scaling, in this case, we're expanding or compressing time. Any guess? So one way to look at it is the following. The old t becomes 2 times the new t. So the new t, the new clock, right, is half of the old t, isn't it? So is it time compression or time expansion? Another way of looking at it is, again, for instance, the old t is -1, right? So if you're not comfortable with this one, let's say this old t equal to 2 times t prime. What we have here is t prime, okay? So previously t equal to 1, so this t prime in this case should be half. So this is our new circle, right? And then our new cross used to be at -1, and now it should be -1/2. So it's right. So you're just changing t, okay? So in other words, this clock, right, is the old t is 2 times the new t. So our clock is like twice faster. So with 1/2, we can finish what used to take as 1. So in other words, you're like changing the unit of time. So you are changing the unit of time, right? It used to be t, now you express it as 2 times t. Okay, so that's a difference. It's just like changing the length from the unit of inches to centimeters. So you are just changing the unit of time. And then in the end, you're doing a time shift. So how do I do the time shift? Apparently, I need to do, let's say I changed t to t minus t naught. Let's say I don't know what t naught is, okay? Then I know that x of -2, now I substitute t by t minus t naught, okay? And I expand it should be equal to x of -2t plus 2 times t naught, right? And I know that in the end, I desire 1. So t naught equal to 1 divided by 2, right? 1/2. Is that right? So what I'm doing here is t minus 1/2. Okay, so this is what you need. So in the end, you need +1, but essentially you are doing this 1 divided by -2, right? So what does it mean? Eventually you need the time shift of 1, but the time clock is no longer like the original t anymore. It was first reversed and then scaled. So time is now running in a new opposite direction and in a new unit. So the original time shift will be changed as well. It will be scaled, right, accordingly. So that's the reason you got to be careful with what is needed here. Okay, so that's the time shift. So you got to be careful with problem 2B, I think, for this one. Okay. Any question for this example? Okay, so in general, you know that if you need a +1, you just divide it by the final scaled and reversed ratio. In this case, it's -2. Okay, if you don't know, just assume it is T naught, and then you can easily derive this T naught. That's the TBA approach in the slides. Okay, so that's the difference. Okay, so if you shift the time first, that T naught is going to be -1. Okay. Okay, so now let's come to the second example. It's about periodicity. So let's look at a few basic signals, but because what else was learned here are basic signals. Okay. So that's something else we have learned. So that's exactly asking you about the basic signals, right? In this case, let's look at an example. Let's look at this one. 5 cosine minus 7t minus pi over 6, or 5 cosine minus 7n. So one is x of t, one is x of n. Okay, are they periodic? What is your answer? Are both periodic? Yes, both are periodic. Because cosine are like sinusoidal. Is that right? Okay. One thing to keep in mind. So in the case of discrete time, we're not just changing the notation from t to n. We seriously mean that the time is now discrete. We are sampling the signal at discrete time. Okay, but we're not recording the signal over the continuous time anymore. Okay. So in the first case, it is indeed periodic. And the period, as we learned before, as we learned before, the period is multiples of 2 pi divided by absolute value of omega naught, right? Where k are integers, okay? Of course, t has to be positive. So the smallest, too many arrows. So t naught is the smallest t, so that's 2 pi divided by 7. That's when k equal to 1. So that's the smallest. Okay. And that's the conclusion we learned before, right? But in this case, it is not. We can see why it is not by looking at the definition of periodicity. It's the following. That means at any n, you can shift the signal by a period capital N, and you can get back to that signal. Okay, so let's see whether it could happen. Okay, so let's call this omega naught in general. Okay, so let's first of all, this is the time shift. It's only shifting the signal left and right. It doesn't change the periodicity of the signal, right? So let's, and the 5 is also scaling the signal vertically, right? At all the time, so it doesn't change the signal's periodicity either. So we can ask in general, cosine omega naught n, right? Or in general, exponential of j omega naught n, which is cosine omega naught n plus j sine omega n. Are they periodic or not? Okay, right? Let's check. Okay, so for instance, let's check this one. The definition said that at any n, and then you can shift this signal by a supposed period capital N, and you will get the same, right? And then on the right, we have cosine of omega n plus omega naught capital N. So how do I make this equality occur? If it's not clear to you, let's look at the right, the complex signal, e to the j omega naught n equal to e to the j omega naught n plus a period, and the right-hand side equal to e to j omega naught n times e to j. So we can factorize it, not capital N, right? Then we can cancel both sides, and then left side only remains 1. So we end up having 1 equal to e to j omega naught n. So on the complex plane, you have real and imaginary. 1 is right here, right? So as you know that we can represent any complex number by its length r, that's a polar form, and angle theta, right? So this is our e to j theta, and our r equal to 1 and theta equal to omega naught n, and in our case it's this point, so this theta is 0 or 2 pi or integers of 2 pi. Okay, so that's something we learned. Similarly, here we have omega naught n equals to integers multiples of 2 pi as well. Okay, because you can just add 2 pi to this cosine, you will get the same. So where k will be integer. Okay, so if we rearrange both sides, we'll find that omega naught has to be k divided by n times 2 pi. Okay, so let's look at it. This means that k is an integer, n is an integer, so the ratio is rational. It's a rational number, right? So, and then 2 pi is a irrational number. that cannot be represented as ratio between two integers, okay? So we learned that, okay, it's only periodic if omega naught is rational multiple of pi. So you can say it's rational multiple of 2 pi, but it means it's also rational multiple of pi. Okay, so apparently omega naught in this case is -7. It's not a multiple of 2 pi, rational multiple of pi, so it's not periodic. Okay, so let's look at another example though. Let's say sine of 2 pi divided by 7n plus 1. Okay, so maybe I should use a different one. 2 pi, yes. Let me use just pi. Let's say it's 7 pi. 7 divided by 2 pi, okay? So in our case, omega naught is equal to 7 divided by 2 pi, right? So, so this is rational multiple of pi. So it's periodic. Okay, then what is fundamental period? Well, still from here, from this equality. Right here. If you assume that omega naught is known, then n is equal to k times 2 pi divided by omega naught, but we add absolute value, right, to make it positive. So in our case, you know, t equal to 2 pi divided by k times 7, and then that equals to 7, 4 times k, where k are integers. But again, t has to be positive and t has to be integer. So what's our fundamental frequency? T naught. The smallest t is when k equal to what? Is k equal to 1? When can I have the smallest period t? That's when k equal to what? If k equal to 1, we have 4/7. That's not a integer. Remember, our discrete time signals are defined over integer valued time. Okay. So what's the smallest k that can make this 4/7 of a k still a positive integer? 7. Yeah, just like Philip said. When k equal to 7, we have the smallest period called fundamental period. That's 4. Okay. And the last example, don't know whether I have time to talk about the last example, is a little bit more sophisticated. So let's say we have the sine of half pi n times cosine of pi over 6n. Okay, so it's definitely more complicated than any examples we have seen so far. How do we address this one? Well, it's first of all, we have a product of two discrete time signals, both of which are periodic, right? Right? Because half pi and 1/6 of pi are both, you know, rational multiples of pi. So, but it's a product of two periodic signals. Would that still be periodic? Well, I think that depends, right? So I'm going to show you one way of solving this problem, but there are different ways of understanding the problem and solving it. I'm going to express it as, I'm going to change the sine times cosine to be the sum of two signals, okay? Because we know the following. Sine A times cosine B is equal to 1/2 of sine A plus B plus sine of A minus B. Okay, you may say, oh, this is a random trigonometry. Am I supposed to memorize it? No, you don't have to. But you can use Euler's formula to derive it very easily because you have, the real and the imaginary part very easily. But anyway, here we are changing the product to sum. So then in this case, we have sine of okay, I have the sine of 1/2 pi plus 1/6 of pi times n, and plus 1/2 of sine of 1/2 pi minus 1/6 of pi n. And then in the end, I have 1/2 of a sine of 2/3 of pi times n plus 1/2 of sine of 1/3 of pi times n. Okay. So again, because of these values are rational multiple pi, I have a sum of two periodic signals, two discrete time periodic signals. 1/2 doesn't matter because it only scales vertically, it scales at every point n. So I have two periodic signals, right? And then, and what are their fundamental period? Well, let's see. So in the first case, let me call it T1, okay? Because we have two signals. So I put a superscript there. Just does that mean it's a square? Well, okay, let's use a different notation. T prime and T prime, or T and T prime. Okay. Okay, so let's say T prime and then T prime prime is equal to K times 2 pi divided by 3 times n. I'm sorry, there's no n. And then the smallest fundamental period is when this is equal to 3 times k. So apparently that's when k equal to 1. So that's 3, right? And the second one is k times 2 pi divided by pi over 3. And then that equals to 6k, right? So the smallest period, fundamental period, is 6 when k equal to 1, right? But now the question is, what's the sum? Is the sum still periodic? Well, you can think of the following. You have one signal that's basically rotating, right, from the 3 o'clock, and then it comes back, it's rotating. It comes back every 3 seconds. Okay, so it's 3, 6, 9. So it comes back every 3 seconds. Okay, and I have another signal. That's the second signal. That is rotating slower. It comes back every 6 seconds. 6, 12, 18, and so on. So the question is the sum still periodic? right? So in other words, would the sum still come back at this 3 o'clock after some time? How do I make that happen? I just make sure that after some time, both the left and the right return to the original 3 o'clock, right? So I just need a time that both return to 3 o'clock. Did you find that time? What's that time? On the left, you see that it returns to 3 o'clock at 3 seconds, 6 seconds, 9 seconds. On the right, you see that the second signal returns to 3 o'clock. It's rotating at after 6 seconds, 12 seconds, 18 seconds. Is there a time point where both return to 6 o'clock, 3 o'clock? It's 6 exactly, right? So it's exactly 6, okay? But in general, right, 12 would work as well, right? 18 would work as well. So in general, any common multiples of 3 and 6 would work, right? For instance, 18 would work because the left signal will rotate 6 times and the right signal will finish 3 cycles, right? So as long as we have, common multiples of the two, we are fine, right? But what is the smallest fundamental period? Well, in that case, we are looking at the least common multiple between these two. Okay? In this case, it is equal to LCM between of 3 and 6. That is 6. Okay? Right? Because, again, let me continue writing here. 12, 15, 18, and so on. So 6 would work. 12 would work. 18 would work. And these are common multiples. I'm just looking at the smallest common multiple, and that is 6.